Good morning to everyone. I am Giovanni Azzone and I am a PhD student of the third cycle, and I attended my PhD under the supervision of Professor Roberto Zanasi, and I can resume my research activity with the title Modeling and Control of Multi-Phase Asynchronous Electrical Motors. Okay, let's start with some outline to resume the main topics of my research activity. First of all, I will discuss about the general POG modeling of a general multi-phase asynchronous motor, then moving on the main field-oriented control techniques that can be applied to this kind of machines. Then I will discuss about a case of study of this kind of POG modeling, that's to say a cascaded doubly-fed induction generator. Then I will move talking about a new complex modeling that consider also into account the harmonic injection. And to complete the description of this kind of systems, I will discuss something about the star and delta connection of the stator phases. Okay, let's start with the first one. As you can see from the picture, this is the general electrical scheme of a multi-phase asynchronous motors, and defining the current vectors and the state vectors, and applying the Lagrangian approach, we can obtain the following dynamic equations. As you can see, the equations are really compact, and they are just put it in a vectorial and matrix form, and they are referred to a static setting reference frame. So after had obtained these equations, we have used state space transformation matrices just to refer the dynamic equations to a new rotating reference frame. The results of this of the application of this transformation has been obtaining a L matrix that is now constant, and this is a nice result because it can be easily inverted for the dynamic analysis of the system. And second, the redistribution matrix, that is the W matrix, has a skew symmetric structure that represent how the energy is redistributing in the system. So using the power-oriented graph modeling technique, we can give this kind of graphical model where you can see the electrical part that is divided from the mechanical part, and the POG gives the chance to structure the scheme in a really symmetric way, just putting in evidence all the energetic parts of the system, both in the electrical and mechanical domain. In particular, you can see the energy accumulation sections for the electrical part and the mechanical part. The same is for the energy dissipation sections. While in the middle, you can see the redistribution section that describes how the energy is redistributing into the system. While in the first part, you can see the transformation matrix that have been applied to the original reference equations. So, another important analysis that have been investigated in this kind of system is the dynamic analysis of the system. That's to say, the calculation of the eigenvalues. The only problem is that this kind of system is strongly nonlinear, so it is supposed not to be able to calculate the eigenvalues. But considering the hypothesis of the mechanical dynamics slower than the electrical one, we can work on a reduced system that is linear, and then we can calculate the eigenvalues. The corresponding eigenvalues are these following four that are depending on electrical and mechanical parameters. And we can also study how they are moving on the complex plane. And you can see on your right two typical way of moving of the eigenvalues on the complex plane. This is a theoretical investigation that we had that will be compared with a new complex system, a new complex modeling, just to putting in evidence the advantages that we will describe in the use of the complex transformation. So, in order to prove the effectiveness of the mathematical model that have been studied, we decided to create a Simulink macro block of the multi-phase motor that describes the dynamic equations in the rotating transformed frame. As you can see, the implementation is really easy because the POG graphical technique gives the chance to map directly the scheme into Simulink, because the structure is so symmetric and is well distributed energetically speaking. The other hint, the other advantages of this block is that it has a mask menu that can be filled with all the electrical and mechanical parameters. This gave us the possibility to use this block to perform any kind of simulation and in any kind of dynamics of the motor. So it is a really nice tool that can be used in any kind of industrial application or simulation, or can be also mapped in D-space systems to have experimental results. And these are some simulation results that can show the effectiveness of the implemented model. On the top part, you can see the evolution of the angular velocity and of the mechanical torque. And in the bottom part of the slide, you can see how the currents are evolving in the time, both in the static reference frame and in the rotating reference frame. Note that in the transformed reference frame, only the first two components are not equal to 0, because the others, whatever is the number of rotor and stator phases that have been chosen. But the other are 0 because they do not generate torque. They are not involved in the generation of the torque. So let's pass to the other topic, that is the investigation or the description of the most important control technique that can be applied for this kind of systems. Just focusing on the field-oriented control techniques that are based on the transient behavior of the system. This means that you can use this technique if some high-speed applications are supposed to be investigated and implemented. And it is based also on the rotor field orientation conditions. This means that we need to orient the rotor flux in order to put the quadrature component of it to 0. This ensures the following control scheme that is called indirect rotor field oriented control scheme. The reason is because the estimation of the stator position is indirect, because it uses the equations that have been obtained with the rotor field oriented conditions. In particular, you can see in the middle the presence of a yellow shaded section that represents the real core of the control, and that will be used also for the other control techniques. The reason is because inside you can see the three kind of PI regulators. The first one is to control the angular velocity of the motor, and the other two are have the role of controlling the direct and quadrature current component of the stator current vector. So let's pass to another rotor field oriented control technique that in this case is called direct, and the name suggests the reason why it is called direct, because now we are estimating directly the module and the phase of the rotor flux by using the following equations that can give us the chance to estimate the direct and quadrature components of the rotor flux and can be implemented in the control scheme. Then the stator frequency can be calculated using the following formula, and the rotor angular position can be calculated using the arctangent function. So the only drawback of this kind of control technique is that we need to measure the angular velocity because it is needed for the calculation of the stator frequency. And the second drawback is that we have to use the arcotangent function that needs a lot of computational cycles to be computed, to be calculated. The solution to all these drawbacks is the sensorless rotor field-oriented control. And also in this case, the name suggests the function of the control. Sensorless means that we don't need a sensor to measure the speed of the motor, the angular velocity of the motor, because it will be estimated. But first of all, let's analyze how we can substitute the arcotangent function. This is typical closed-loop system that can be implemented in order to estimate the angular position and stator frequency without using an arctangent function. And this is the first simulation results that shows how the angular position calculated using the arcotangent function and the one calculated using the closed loop system, they perfectly overlap themselves. So we can easily substitute the arctangent function with the closed loop system. But the real core of this control is the estimation of the angular velocity. Using that formula that include inside the estimation of the stator frequency can give us the expression and the values of the angular velocity. And these simulation results, you can see how the measured and the estimated angular velocity, they are overlapping. And the dynamic of the estimation of the angular velocity depends on the controller that is inside the closed loop system. Of course, this kind of technique is preferable to the others, but of course it's much more complicated because we need to implement a lot of formulas inside without forgetting that we need to put inside the blocks to perform the transformation from the static reference frame to the rotating reference frame. Okay, so let's pass to another topic that is a sort of case of study of the previous power-oriented graph motor modeling. That's to say the cascaded double-fed induction generator. That is a system widely used for wind turbine systems. And it is characterized by an external torque that is applied to a turbine and that is provided by the wind and that is transmitted to a shared rotor shaft that belongs to two different three-phase induction motors. The first one, the blue one, that is the controlled motor one. And the second, the green one, that is the motor that will be used to supply a constant voltage and frequency grid. That is the main goal of this structure. Without forgetting that we had the chance to decide how the rotor phases have to be connected in order to shape the torque function. So this is the structure of the system, and in this image you can see the electrical scheme of the system. Where, as you see in the middle of the figure, there's a matrix that is called S, and it describes how the rotor phases can be connected by selecting three alpha parameters. In this way, we can decide how to switch the three phases of the common shared rotor. And we can also define the following dynamic electrical equation of the system. As usual, you can see really compact form and vectorial matrix form that, to tell the truth, inside all the matrices have a really big and complex structure. So, using, again, the Lagrangian approach and using the power-oriented graph modeling technique, we can obtain the following graphical representation, where you can see the electrical part and the mechanical part divided by the connection blocks. And as usual, we used an orthonormal transformation matrix to refer the dynamic equations to a rotational reference frame. In this case, the transformation matrix is much more complex because we need to take into account the first stator, the second stator, and the common rotor that is shared between the two motors. So, we need also to implement a control law, and we decided to implement an indirect field-oriented control. The goal is controlling the first motor in order to obtain a constant frequency and voltage power on the second motor. So this is a typical scheme of an indirect field-oriented control that will be applied to the first motor. On your right, you can you can see the field-oriented control equations implemented in the control scheme. And in particular, just tracking this speed reference, we can ensure the output of the system a controlled three-phase voltage that will be supplied to the first motor in order to obtain a constant power grid on the second one. And also for this case, we implemented a Simulink macro block, but in this case considering not only the cascaded double-fed induction generator system, that is the yellow one in the middle, but also an electrical load, the implemented control, and you can see also the reduction gear. This means that we decided to take into account also the external part that is composed by the wind turbine that is perfectly coupled with the shared rotor. And the correspondent simulation results are results are the following one. On the top one, you can see how the second motor stator voltage, after a brief transient, is settling on constant frequency and voltage. Voltage, that is the real goal of the control technique. And in the bottom part, you can see the control variables that are settling on the reference that we have imposed in the control strategy. So now I would like to describe the second part of my research activity. That's to say, a new modeling that we can apply, we can describe for multi-phase asynchronous motors. That consists in using a complex transformation matrix and in taking into account also the odd harmonic injection. About the second detail, we can consider the odd harmonic injection by considering the hypothesis that stator and rotor phases have a concentrated windings structure. That's to say that now the self and mutual inductance matrices have not a cosinusoidal shape anymore, but we can decide how to shape them just considering them developed like with Fourier series. So giving the right weights to the Fourier series coefficients, we can decide first how many harmonic injection we want to inject in the system and how much they have to appear in the final formula of the mechanical torque. And the first aspect that we described was the fact that we are using now a complex transformation matrix. That you can see it's much more structured, and mathematically speaking, it is a complex transformation. And I will describe how and why we decided to use this transformation. So the resulting equation system in the new transformed complex rotating frame is the following one. And as you can see, the structure is so compact and is not so complicated, but despite the use of a lot of aspects, just like the complex transformation, the harmonic injection, but also without forgetting that this system is referring to a multi-phase case. So here is the first important benefit in using the complex transformation matrix. In this way, we had the chance of reducing the number of internal space variables. We pass from an ms plus mr plus 1 to ms plus ms divided by 2 plus 2. This means that if we have a 5 stator and rotor phase motor, we have not to consider 11 state space internal variables, but 7 space internal variables. This means that in an hypothetical dynamic analysis, the calculation of the eigenvalues or in the definition of the properties will be really simplified. And this is about the use of the complex transformation matrix. Talking about the use and the consideration of the harmonic injection, this is the first advantage. We can see that now the mechanical torque is also depending on two new terms, the n term and the an. The n indicates the number of odd harmonic that are injected into the system. The an describes the weights that we are giving to the mutual Fourier series coefficients. So we can see two new degrees of freedom that we can use to manipulate or to shape the torque and to achieve a torque enhancement that is really important, because in this way we can consider the multi-phase machine really suitable for high power application. And okay, this is as usual the power-oriented graph model. The structure is the same. Okay, you can see that now the transformation matrices are complex. The presence of the real block to transform the complex part to the real one. And the only difference is that now the green shaded section is the electrical part, but it is composed by complex variables, and it has a reduced order because the use of the transformation matrix. And here is the another advantage in using the complex transformation matrix. That's to say, in the calculation of the eigenvalues. As usual, we need to take into account the hypothesis of mechanical dynamics lower than the electrical one, so we can work on a complex reduced system that is linear, and we can calculate these eigenvalues, S1 and S2. But the real difference is that now we have not to calculate 4 eigenvalues, but 2 eigenvalues, because the other 2 are the complex conjugate of the first 2. So we have a big simplification in the calculation, because studying how they are moving on the complex plane is really hard, because they are depending on a lot of electrical and mechanical parameters. So having the chance to pass from 4 eigenvalues, the study of 4 eigenvalues, to the study of 2 eigenvalues is dividing the effort in the calculation. So this is one of the biggest advantage in using the complex transformation matrix. While about the using in consideration of the harmonic injection, you can see from some simulation results that the torque is increasing, especially in the part of the peak torque, but also smaller, but it is visible in the part of the steady state torque. And this is, well, I think, better visible in the 3-dimensional representation of the mechanical torque. You can see how the mechanical torque in the peak part is increasing, because we are increasing the harmonic injection. And the same is for the steady state, but it's roughly visible with respect to the peak zone. While the electrical vectors are just changing their shape, because we are considering the odd harmonic contributes. For instance, for a 5-phase motor, we have to consider the fundamental component and the third one, and going on increasing the number of phases. So let's conclude the complete description of the system, just talking about some consideration in the star connection and delta connection cases. These are the dynamic equations of the system in the compact form, and we had demonstrated that we have proved that in this case, the last stator and rotor equations can be disregarded and then can be removed from the system. This means that it doesn't matter if we are talking about, we are considering a star connection configuration or a delta connection configuration. The internal model, the internal part of the system do not change. So we can use the same model, that is this one, that is the most general one, to describe a multi-phase asynchronous motors, considering the complex transformation matrix, considering the odd harmonic injection, and simply adding a transformation matrix in the beginning to decide if the stator phases have to be star connected or delta connected, without changing the internal model of the system. This is the most general modeling of the system, and can be really used for any kind of simulation of systems, of any kind of, for instance, for high power application, for propulsion, for wind turbine, and any kind of industrial application where we have to consider all the aspects, such, for instance, the harmonic injection, because nowadays it's really spread all over the state of the art of this kind of machines. So I would like to conclude saying that my research activity has focused on the general modeling and control of the most general case of asynchronous machines, starting from the real modeling and analyzing all the aspects linked with them, and describing the control techniques applied to them. So we decided to model a case of study, that is the generator that used 2 3-phase asynchronous motors, and then modeling and controlling it. And the second part, we focused on a totally new complex modeling that has considered the harmonic injection together with the use of the complex transformation matrix, and also the possibility to switch from a star connection to a delta connection configuration. So my presentation is finished, and if someone of you has some question, I'm ready and available for the answers.